A farmer discovered his horse was extraordinarily intelligent. You could ask it an arithmetic problem and it would tap out the answer with a hoof. Researchers were fascinated and tested the horse. They discovered the horse understood algebra, Euclidean geometry, calculus, and even group theory. However, when they gave the horse problems with Cartesian coordinates, it just stood there dumbly, like any horse. This was quite surprising, given how intelligent the horse was otherwise. They brought in an expert who examined the situation and explained the problem. Of course, the horse cannot understand any Cartesian coordinates you show it. You are putting Descartes before the horse. And if you knew Descartes invented the Cartesian coordinate system, then that makes that joke kind of funny. And we will be using the Cartesian coordinate system to do scatterplots. And what are scatterplots? They show the relationship between two quantitative variables on a Cartesian plane. And that's his name, Descartes. He also said, I think, therefore I am. Now, on the horizontal axis, you have the explanatory variable. Usually that's if this behaves this way, and then we have our response variable on the vertical axis, and then you get the other thing. All right? When we place variables on the axis, that represents how we think about them. We might end up placing them incorrectly, so how we place them really doesn't determine causation. We still need to do our experiments to determine causation. And by the way, each point on the scatter plot represents a data point. So let's go ahead and practice looking at explanatory and response variables with a couple of examples. So the response variable is the one that will go up or down depending on the explanatory variable. I think sometimes it's easier to look at the response variable first to say which one's going to change because of the other one. So if we have t-shirts at a store, do you think that the price is going to change, or the price will change based on number, or the number will change based on price? Well, if it's at the store, the prices of the shirts aren't changing. So the thing that will change will be the number sold, all right? And you would expect the number sold to be higher for lower priced items. So we're saying the number sold of t-shirts is a response based on the price of the shirt. For skin diving, if we did water pressure, you could say, okay, that's going to be dependent on how deep you are. Now, in the book, they actually said, depth is dependent on your visibility. You could argue the other way around. So they're both related, and so sometimes these can be switched. For lightning strikes, you could say that really the response is the time delay of how long it takes to hear the strike. And you've heard that the longer it takes, well, that means you're further away. So it depends on the explanatory variable, the distance. The brightness is the apparent brightness that you can see is your response based on how far you are from the street light. And then cars will say, oh, maybe the age of the owner depends on the weight of the car. You could argue the other way around. I don't think there's going to be a strong relationship here. Okay, so once we've determined explanatory and response variables, the next thing we like to look at is direction. And there basically are three answers. You have either a positive direction based on a positive relationship, and negative direction based on a negative relationship, or nothing. And so those will be your three answers on direction. Either there's a positive, a negative, or nothing. All right, so let's go back to our examples. And I've circled the explanatory variable because it's easier for me to think of direction and the other. So I got to start with the price first. And do I think the number sold will go up or down when the price goes up? I think the number sold will go down, all right? So cheaper shirts will sell more expensive shirts will probably sell less. If it's just plain old t-shirts, okay? For skin diving, since the depth is the explanatory variable, as the depth increases, we expect the water pressure to increase. So that's a positive direction. When the visibility increases, that must mean that my depth is going down. I'm getting closer to the surface. When my distance increases from the lightning, I expect my time delay to go up, and that would be a positive correlation. When my distance from the street light increases, I expect the brightness to go down, and that would be a negative correlation. And finally, we really don't have any direction for weight of car and age of owner. There's no real good relationship there. Now you're going to see basically three forms of scatter plots that we're going to deal with in this course. There's the straight or linear, and that can be positive or negative. It could be curved, or maybe there's no pattern at all. And occasionally you might see some exotic patterns like this, but that's beyond the scope of this class. Then finally, there's the strength of the scatter plots, which is either stronger or weaker. The closer you can get this correlation, so it looks like a line or a very, you see this pattern, a strong pattern, that means it's a stronger correlation. If it doesn't stick to the pattern as well, it is weaker. So we're going to go ahead and look at those same examples and try and determine what we think the form and strength would be for each one. So for our t-shirts, there's probably a linear correlation. So as the price goes up, we sell less. It could be curved, but we don't know. It depends. And we expect the strength to be moderate. Okay, maybe not super strong, moderate. And then, again, this is a guess. If we had the data, then we could determine if it was actually strong or not. For depth, we do expect a linear relationship, and we do expect it to be strong because there's a very strong relationship between how much water pressure you have and how deep it is. For depth and visibility, we expect it to be linear. It could be curved, by the way. And weak to moderate. Why is that? Well, there could be other reasons that visibility is not as high, or you might have poor visibility at a shallow depth because there's just more muck in the water. For lightning, time delays of lightning, we expect that to be a linear relationship and strong. So the closer you are, the shorter the delay, and it should be very correlated. For a street light, that's actually going to be curved. It's sort of an attenuation thing, and you haven't learned that. You could have said linear, and there would be no reason for me to argue with you based on the information you know. And it should be pretty moderate, because you can still, when you get the further away you get from a street light, you can still see it, and it takes a while for the brightness to change, your apparent brightness anyways. And then again, the cars, there's no shape, and it's very weak because really there's no relationship there. The one last thing you want to look at are unusual features, which are like outliers. So you can see up here we have an outlier highlighted. And if you have clusters or subgroups. So we're really going to get into that more later in the next chapter, but those are things to take into consideration. Now your TI-84 is actually quite good at plotting scatter plots. So to do that, first of all, you need to make sure you get stat and enter to edit. Now we can actually name the data so it matches. So you're going to arrow up, get to these headers, and go right till you get an empty one. And then you hit the alpha key, and we're doing an example on page 20, which is fat and calories. So we're going to enter the name fat and hit enter for this column next to L6. Okay. And then we can arrow over to the next column and do the same thing. And I'm going to put calories and press enter. Notice how it said exact. Just go ahead and hit edit there and make sure that you're entering it and editing it, and then use the alpha keys to put in CAL for calories. Okay, this, by the way, this is number 20 from page 164 in your book. Okay, now we enter the data for both columns. So I'm just basically entering the data from that problem. We got 19 calories, 31, 34, 35, 39, 39, and 43. Then we go to the next column and enter in the calories. And so when we had 19 grams of fat, 410. Then 580, 590, 570, 640, 680, 660. And those are all the data points. By the way, if you don't match these, you're going to get an error. So make sure you have the same number of X and Y. All right. Now you go hit second stat plot and set up one of the plots for Scatterplot, which is your first choice right there. Hit enter. And then we can come down and use second list to actually change the name so we don't have to remember L1. So it's second and list. There we go. And you scroll down and you can see calories, which is the name we entered. So that's sometimes handy. And then you can do the same thing for Y list. Scroll down and now we'll put fat. So the explanatory variable is calories and the Y list is fat. In this case, we could have really gone the other way around, but it'll work well enough for this example. And you can see that here's our graph. And then you can also hit trace to see the different values. All right. So if I go to the graph here, you can see the direction's positive. And you notice it didn't matter if I had fat and calories or calories and fat. The form is linear, and the strength is actually pretty strong, I would say. The only unusual feature, we haven't really talked about it, there is sort of a gap here, which makes this point kind of special, gives it a little added weight, and we'll talk about that in a future chapter. So the practice problems that are relevant for this part of the lesson are in the back of chapter 7, problems 1, 3, 5, and 9. Go ahead and check those out and check against the answers